Welcome. I'm going to present our work developing a library for general probability in Coq. This is joint work with Barry Trager, and we are at IBM Research. By general, we mean that we want to handle not just the simple discrete spaces, but the larger class of measurable spaces. And Coq is an interactive theorem prover. An interactive theorem prover allows us to encode mathematical statements and their proofs in a way that a computer can both assist and verify that the final proof is completely correct. It's been used for some notable achievements, such as a fully verified proof of the four-color theorem, of the Fate-Thompson auto-order theorem, and to develop ComCert, a formally verified compiler from C to assembly language. In terms of probability, in this talk I'm going to give an overview of some of the probability definitions and theorems that our library supports. And I'm going to start by giving some simple things that we do and give a flavor of what they look like when encoded as Coq definitions. So let's start with a very primitive notion of a pre-event. A pre-event is just a set. So looking at the top line, we define it in Coq by saying definition pre-event. So given some type, which we're going to call t, it's a function from t to prop, which means it's a predicate over values in t. i.e., we're going to define a set by its characteristic function or membership function. So if any element that satisfies this predicate is going to be deemed in the set. We can then define an example of a pre-event or set is omega, right? Pre-omega is the universal set which everything is in. Given a set E on the next line, we see that we can take its complement by saying, okay, given an element, let's see if the predicate E is not satisfied by that element. And similarly, given a countable collection of pre-events, which we model here on the last line by saying it's a function from the natural numbers to a given pre-event in that collection, we're going to say that an element x is in that union, countable union, if there exists some index such that the pre-event at that index indeed contains that element x. Now that we've defined the basic idea of a pre-event, we can define a sigma algebra over pre-events. So a sigma algebra over a type T comes with a predicate, sa sigma, that determines whether a given pre-event is in fact in the sigma algebra. So similar to what we did before, we're going to define the set of measurable sets. Then sa all says that the pre-omega, the universal set, has to be in the sigma algebra. Sa complement is going to require that given any pre-event A, if it is in the sigma algebra, so is its complement. And sa countable union is going to encode that given any collection, or countable collection, such that every element in the countable collection is in the sigma algebra, then their union is also in the sigma algebra. Putting these together, we get that any instance of the sigma algebra type class has a sa sigma predicate, which is known to satisfy the important properties of a sigma algebra. Now, this right here is the basics of defining measurable and probability spaces. But before we jump to that, we found that there's one more definition which is helpful, which is we're going to here define an event over a sigma algebra as, and that notation there is Coq notation for, an element x, which is going to be a pre-event, along with a proof that that pre-event is satisfies sa sigma. In other words, if that pre-event is in the sigma algebra. This is useful because it winds up that a lot of operations, such as union, intersection, and many others, preserve that something is in the sigma algebra. And so we can lift these two events, and then we don't have to keep threading through these proofs that things are in the sigma algebra on the side, but they're just baked into the notion of an event. Using these, we can now define the notion of a probability space. So recall that a probability space provides a non-negative measure, which is a function from events to reals, that satisfies countable additivity, and if you take the measure of the entire space, then you get 1. So as before, we can define this as the type class over, in this case, a type T and a sigma algebra over that T. And we're going to give, it comes with a probability function we call PSP, which maps from events to R. Now notice that because PSP maps from events to R, we only have to define it for things which are measurable. And of course, we, as before, then add additional fields that encode the properties of countable additivity, that they add to 1, and that it's not negative. But those are elided in this talk. Given these notions, we can now define a fundamental concept, that of almost surely predicates. So we say that with respect to a given probability space, a predicate P almost surely holds. What we want to say is that it almost surely holds if its probability is 1. We can't quite say that, though, because we want to use this for any set or pre-event, and not all of them are measurable. So what we actually say, in order to weaken this, is we say there exists some measurable set, some event X, which is contained within P, such that that event has measure 1. We could alternatively and equivalently say that the set of points that don't satisfy P have measure 0. That by itself is already a very important definition, but we can then lift that to relations by saying, given a relation between two elements of a target domain and two functions from some source domain to some target domain, we can say that almost R2 of that relation is, well, if we take those two functions, apply them to a single point in the source domain, and the relation holds, then if that's almost the case over the source domain, then we say that the almost R2 of the relation holds. This allows us to lift binary relations such as equality or the less than or equal relation on reals into almost relations. This is particularly useful because the almost R2 lifting preserves many important properties such as reflexivity, being a pre-order, a partial order, other things like that. So almost R2 RLE is automatically a pre-order because the real less than or equal relationship is a pre-order. Additionally, these things are often morphisms for common operations like addition, subtraction, multiplication, division. So if two things are almost less than or equal and you add them to two things almost less than or equal, the result are almost less than or equal. Rather than having to unfold the definition of almost R2 and look into this existential, the event that's contained within the larger set of things that are satisfied by the predicate, we try to reason at a higher level, and there are three lemmas in particular that are really useful for this. The first one, called all almost, is pretty trivial. It just says that if a predicate unconditionally holds, then it almost holds. The next one, almost impulse, says if it's almost the case that P1 implies P2, and it's almost the case that P1 holds, then it's almost the case that P2 holds. This is powerful because what often happens is you have two assumptions that you've proven via whatever techniques, and one of them says that almost P1 holds, another says almost P2 holds, and then you have a goal you're trying to prove, which is almost P3. So you can use almost impl twice in that case to get that what you need to prove is that almost of P1 implies P2 implies P3. Then, in many cases, it winds up that that particular set of implications holds unconditionally, and you can use all almost to reduce it to simple logical reasoning as you would do otherwise without the almost. One other thing lemma that's particularly helpful is almost for all, which says that in fact if you have a countable set of pre-events such that they all almost hold, then it's almost the case that they all hold. And this allows you to then, combined with almost impl, push down a countable collection of these almost statements. Now that I've presented some feeling for what these definitions look like in Coq, I'm going to step back and give a higher level overview of some of the other things that we build in our library. So on top of the tools that we've just shown you. So we define what it means to be a measurable random variable. So a random variable is between a source type and a target type, both of which are equipped with sigma algebras. And we say that it is measurable if given any event, meaning anything in the sigma algebra of the target domain, if we take its inverse image under the random variable, if that is measurable, meaning it's in the sigma algebra of the source sigma algebra. This can be seen as a generalization of continuous functions. Using this, we can then define expectation for measurable random variables. This is essentially the Lebesgue integral, and we do this in the traditional way. So we start by defining simple expectation, which is for the set of random variables which have a finite range. So the image of the function has a finite. Then, and we do that essentially just by essentially discrete calculations. Then this can be generalized to any non-negative function by approximating the function within a limit of finer and finer simple finite range functions. And then we can do it for general functions by looking at the expectation of the positive and negative parts and then subtracting, assuming the difference is well defined. And we can prove the various usual convergence limit theorems, such as monotone convergence and dominated convergence. One thing I'll note is that while I presented everything as over R, the reals, in fact, we discovered that it is a much more natural setting to use R bar, which is the extended reals. So that's reals where you add positive and negative infinity. And we extended various underlying things like limits to work with extended reals, and then we defined a version of expectation that works over extended reals. And this actually simplifies statements of things like the monotone and dominated convergence theorems. On top of this, we can then define LP spaces. An LP space is the space of measurable functions whose LP norm is finite. So the LP norm is where you take the absolute value of a function, raise it to the pth power, and then take its expectation. You then take the pth root. But the point is, if that expectation is finite, then that function is in the LP class for that p. Now there's a technical point here where in order to make this an actual norm, we have to identify functions that are almost equal. And that's because we need a unique concept of what 0 is. And because we're using expectations, things that are almost equal have the same expectation. So we need to do this quotienting. Once we've done this, we find that these are all module spaces. And for p greater than or equal to 1, they're in fact complete normed vector spaces. And in particular, L2 is a Hilbert space. This is a particularly important fact because we use it to define conditional expectation. Conditional expectation can be thought of as the best approximation of a function that's measurable with respect to some smaller sigma algebra. Now, for L2 functions, this can be defined via projection over L2, and that works because it's a Hilbert space. Then for other L1 and general for basically other measurable random variables that have finite expectation or that are not negative, we can define conditional expectation via a limiting argument, similar to how we built up general expectation, where we approximate the functions with L2 functions. Because L2 is a quotiented space, note that the conditional expectation is not unique. So most theorems only hold up to almost, like things are almost equal or almost less than or equal. Some highlights of things that we've proven in our library are the strong law of large numbers and the martingale convergence theorem, also known as the fair games theorem. These are particularly interesting because there's a list going that Fabrique maintains of like 100 theorems that would be interesting to see formalized. And so we are the first ones to do it in Coq that's entry 59 and 62 here. In fact, at the time that we started this, we were the first ones to do the fair games theorem. No one had done the fair games theorem, and only the law of large numbers had only been done in Isabelle, although the Lean team is also working hard, and Lean is a different interactive theorem prover, and so they have proved those two as well. We have used this for a couple applications, particularly in machine learning, which is the goal of our library, to be able to use this to prove theorems for machine learning applications. So we have a paper on formalizing the convergence proofs for value and policy iteration, and we're working on extending this for more general Q learning. We also have a paper that will appear in ITP on formalization of Dvoretsky's stochastic approximation theorem. This is a very general framework by Dvoretsky, and amongst other things, it can be used to prove the convergence of the Robbins-Monroe. Our library is open source and publicly available. It is an ongoing research effort. If anyone is interested in using it or anyone interested in formalizing their own work in probability theory or machine learning, we encourage you to give it a try and reach out to us. It's an ongoing project, and collaborations and contributions are welcome.